Okay, YouTube, in this video we're going to be exploring the inverse properties of exponential functions with logarithmic functions. And so let's go ahead and start by talking about what we mean by a logarithmic function in the first place. We've seen exponential functions. As a matter of fact, what I'm going to do is I'm going to indicate that exponential functions, okay, we've seen up until this point are functions of this form y equals a times b to the x. And so I'm going to simplify this even further. In this video, let's go ahead and allow our a value to be equal to 1. We say that this is our primary exponential function. Then we're going to say that by definition of a logarithm, it follows that the logarithmic function g of x here is equal to log base b of x is the inverse of this exponential function. And so what we're going to see is that going forward, okay, logarithmic functions are the inverses of exponential functions. And in this case, they're saying g of x. I'm going to write this as y equals, but they say log base b of x right here. And so we'd say that these two functions are by definition inverses of one another. And so we're going to use a special property of inverses to undo each other here, or at least to say that inverse functions undo one another. So just to show you really quickly how these are truly inverses, if you were to rewrite, okay, this logarithmic expression exponentially, then we would get this. We would get b, to the power of y equals x. And so what you'll notice right off the bat is that x's and y's are switched. So in other words, what's being switched here is that we have a domain and range switch. Okay. So if the domain and range are switched here, then these truly are inverses of one another. But by the definition of functions, we're going to get something that undoes the other thing. So let's go ahead and assume that we have two functions here. And what we're going to do is instead of y equals b to the x here, we're going to change this to f of x equals b to the x, just to be kind of consistent with what they're saying over here in the table. So f of x equals b to the x instead of y equals b to the x. And we'll call this g of x. G of x equals log base b of x. But because this is an inverse with this, then we could say that truly by definition what's going on here is that we're taking an input value. This is our domain of our original function. How about I just put it this way? This is some x value here. And what we're doing is under the relationship f, under the function f, what we're doing is we're mapping it over to some y value at that x value. So when we plug in x, it goes over to this y. What we're doing under the inverse relationship here, and we would say that the inverse, okay, g, we'd say g is the inverse of f. Then truly, if that's the case, then if I were to take f of x here, okay, and plug it into g, then I would actually get sent back to x. Okay, so in other words, and I suppose I shouldn't have listed that there, we would say under g. I didn't mean to erase all that. We would say under g here. Then what happens is when we take f of x and we plug it into g, okay, we get sent back to the original x value. And likewise, one thing I want you to notice is that the domain of our original function f here is this x value on the left, and its range is this y value on the right. When you look at g's domain and range, we would say that really what we're doing is we're plugging all of the range values from the original into this inverse function, and by definition it's supposed to send it back to the original domain values, which now becomes the output of our inverse function. So we would say that the domain and range here, really between these two relationships, just switch. And we would also recognize that if this is on the original function, then f of x comma x is on the inverse function, because we would plug this in and get sent back to x. So the profound implication here essentially is this. If we take f of x and you plug it into g, or in other words, if you take an exponential thing and you plug it into a logarithmic thing, then what you're going to get is some cancellation going on. And so we would say, in general, generally speaking here, if we were to take f of x and g of x, which are these inverse functions right here, and we were to plug f of x into g of x, okay, so we say g of x, remember g of x is log base b of x. If we were to take f of x and plug it into this wherever we see an x, then this would become log base b of what? Well, what we're plugging in here is f of x. And because we know what f of x equals, then we would say that this is the same thing as log base b of, and our f of x here, f of x, remember, up here is b to the x. So we'd say b to the x, and what we get really then is just x. Because what we've done is taken the y values from one function and plugged it into the inverse function, we always get sent back to the original input, but it comes from this profound statement right here. And so you can see that our first property is that the log base b of b to the x is x. Now our second property would say, well, what if we take g of x and we put this logarithmic thing and put it into the exponential function? So f of x, remember f of x is b to the x. So if we were to say, take out my x here, and instead what we're going to do is we're going to put in g of x. Then what we're going to get is this b to the power of g of x, which g of x was log base b of x. And so now we get this statement here that undoes one another. I'm going to put a box around this, but it's the same as the second statement you see right here. But both of these statements are relatively profound because what we're seeing here is this. We'd say that exponential functions, okay, and logarithmic functions undo one another. So to recognize when this happens, when they have to undo each other, you're going to see something like this where in the first statement, okay, we're taking a logarithmic thing of an exponential thing, but they have to have the same basis. As long as we take log base b of b to the power of something, then our log and our exponential thing cancel out and we get left with just the x right there. Likewise, if we were to look at these over here, we'd say b to the power of what? Well, b to the power of a logarithmic thing. So exponentials, logarithmics, they undo one another. If you take an exponential thing to the power of a logarithmic thing and they have the same basis, then what you're going to see is that your exponential thing and your logarithmic thing cancel out and you just get left with x. So what I want to look at here is using these properties here to help us simplify these logarithmic expressions, starting with letter A. And letter A, what you see is this. We have 10 to the power of log of 4. So one thing that I want to say about this before we go any further is that this log here, this is the common log. Because we don't see a base here, then really we could rewrite this as log to the power of log base 10 of 4. So the thing that's important to recognize is that we have an exponential statement, 10 to the power of something, but in the exponent we have a logarithmic thing. So when we have 10 to the power of log base 10, what's going to happen is that our exponential thing and logarithmic thing cancel out, and all we're going to be left here with is the argument on this right here. So we would say 10 to the power of log base 10 of 4 is 4. Now, this makes reasonable sense given the fact that if we were to take 10 log base 10 of 4 and rewrite this in a logarithmic format, then we would have said, well, log base something of something is something. And we could see that with this circular relationship here, on both of these statements, our base is 10. So we say 10 to the power of this thing, and our thing that we're putting over here is log base 10 of 4, turned into this unknown thing. Well, hey, if log base 10 of question mark equals log base 10 of 4, then you could see that really we should be getting 4 for the question mark. So it's more, it's the expected thing that we'll write, hey, an exponential thing to the power of a logarithmic thing. As long as they have the same basis, they just cancel out. You get left with this argument here. So for letter B, I want you to see this on letter B. I'll try to make some room here. We have log base 5 of 25 to the x power. So the thing we want to notice is this, log base 5 of 25 to the x power. We have a logarithmic thing, log thing, of an exponential thing. So when you take the logarithmic thing of an exponential thing, then as long as they have the same basis, they cancel out. And so the interesting thing here is that 5 and 25 do not share a common base. But this is often the case. You see something like this where we could take 25 and rewrite it so that it does already have a base of 5. And so if we said, well, do you recognize that 5 is a power of, or sorry, 25 is a power of 5? Yeah, well then we'll say then let's rewrite it as 5 to the power of something. In this case, we get 5 to the power of 2. So using our laws of exponents, remember that if we have x to the a to the b, a power to a power, that we have to multiply our exponents here. This is our power to a power property. Because I have these two exponents here, then I have to multiply those together. We're going to get the same thing as log base 5 of 5 to the 2x. So now because we have a logarithmic thing of an exponential thing, and they have the same basis, they're going to cancel out, and what we get left with here really is true x. Cheers.